pleasure to be an invited speaker in this conference. I have to thank you all for inviting me and assigning me such a nice argument that has been one of our hot topic for several years here at the Department of Civil Engineering, Environmental and Building Engineering at the University Federico II in Naples. I'm sorry that I couldn't be present. I have been in Asia just this month, 1 week ago, and it was difficult for me to be back after such a short period. So, therefore, I will start my talk and I will share my PowerPoint presentation with all of you, where I have summarized the talk on flood risk assessment at large scale, challenges and strategies that we have tackled, let's say, for addressing flood risk in data scarce environment. Now, let's start with the presentation if possible. I share my screen. Here it is. So, again, good afternoon. It is really a pleasure to be an invited speaker at this conference on Eagles of River. And I have to say that the Naga University has been in contact with us in the recent years for a joint collaboration with the University of Naples for hydrological monitoring activity. And I look forward to build new initiatives for the coming future. So the talk of today will be on challenges and strategies in flood risk assessment. And let's start from the beginning. So this is a short introduction about the talk, about the aspects that will be touched in this talk. We will, first of all, I will give a short introduction on global flood risk assessment, then try to identify the main aspects that are impacting on the changes and expected changes in flood risk in the coming future. Then we will move and focus on methods that we have developed and that have been developed worldwide in order to address flood risk at large scale with rapid mapping. We have recently introduced some new metrics for enhancing the capability of geomorphic flood index to describe flooding. Then we will move to another topic that is complementary, but is now the new direction that we are taking, and that is very promising in this context, which is the use of remote sensing for flood risk assessment. In this context, we are moving the technologies from the simple use of geomorphic feature to moving to the use of remote sensing data within a machine learning technique in order to build new flooding maps and flood susceptibility maps. Then we will also recall the potential use of flood inventories that are available, that are mainly based on available information from remote sensing. And finally, we will underline the importance of this data for flood managing and flood mapping. Let's focus at first on the topic of flooding. Based on this document, our world in data, essentially floods can are in numbers and also in terms of economic losses one of the most significant natural hazards at the global scale. The impact of these events is particularly disruptive and is producing probably one of the largest economical damages, along with storms, which are somewhat connected. They are clearly interconnected. Now, we have to understand why, we have to understand what is happening in this context. And let's see, first of all, one signal, one tendency, which is the tendency of water vapor in the atmosphere measured over the last 30 years. If we look at the water vapor over the last 30 years, we will identify and recognize that the water vapor is increasing significantly. And this is the signal of the anomalies of the water vapor, which is increasing because of the climate change, and mainly because of the change in air temperature. The increase of the air temperature is somewhat responsible of a larger amount of water vapor in the atmosphere that is producing larger or more extreme flooding. Let's see, first of all, what is the overall general situation in terms of flooding at the global scale. Then we will move step by step on this topic. We'll try to identify more and more details. First of all, we have understood that the problem of flooding is significant. Here we have I have provided a review of the literature in this context, in the context of global flooding assessment. And there is this good publication by Dinley, which actually states that only 1/3 of the globe is actually affected by flooding of different magnitudes and with different probabilities. But this portion of the world is somewhat the most populated one, with a significant part of the global population. Of course, there is a subset of this data which is the subset where most frequently flooded area, which represent 9% of the land. And this part of the globe covers about or includes 38% of the global population. In this context, there are major rivers and lowlands in South and Southeast of Asia, which are affected by significant flooding. In this list, there is Bangladesh, China, Indonesia, and the Philippines as well, and also Eastern Africa, Europe, Central America. And so these are all somewhat influenced by the presence of flooding. In the recent years, we're observing a number of flooding, which gives us the perception that flooding are increasing. Now, this might be true, this might be not. This is probably unclear up to now, but we will try to say something also about this. For sure, there are events like the event, the Medicane, occurred in 2023 in the Mediterranean area that led to the destruction of two dams that actually affected the city of Derna in Libya. And this produced a massive destruction, which was particularly impacting on local society. So there have been events like this, and these are not isolated, because we are observing with time and over time, especially in area where I have more information, more data in order to reconstruct a repository of data. There is an increasing number of evidence of extreme events which have rainfall amount that are comparable with the amount of rainfall that can fall in a city or in a region in a month or even in a year. Like if, for instance, we look at the rainfall event of October 2009 in Messina, they received a rainfall event of 500 millimeters in 24 hours. So these are really exceptional events which are classified as extreme or extraordinary events. But the strange thing and the strange fact is that those type of extraordinary events is becoming more frequent respect to the past. And what is the global situation? How these extreme events are impacting, are present at the global scale? There is a decrease, an increase in the reality. Floods are causing millions of fatalities and losses for tens of billions of dollars. Now, the question is, can we associate these events to a change in hydrological behavior, or there are other mechanisms that are producing those events? In the reality, there is this paper by Merz, which is an illuminating one, which is suggesting that there are also different mechanisms, such as recurring circulation patterns of climatic forcing or failures of flood defenses that may lead to extraordinary events and extraordinary damages. Now, at the same time, there is also a clear reduction of fatalities and population affected after mid 1990, which was mainly due to a significant effort for risk reduction measures. There is more awareness nowadays. There have been a lot of flood detection structures and so on. Of course, on the long term and in the future, there is the expectation that the flooding might increase in many regions, and especially in Asia and Africa, due to two factors. One is the climate, and the other one might be the socioeconomic change. Let's have a look also to another paper. In this paper, more recently published in Nature Communications by Rentschler, there is a global perspective in flooding, and there is the evidence that the first 10 most exposed countries have more than 33% of the population exposed in high flood risk, which is a critical aspect. In this context, there is one exceptional case, which is represented by the Netherlands, which is actually is putting in action a significant protection standards that allow to have a significant reduction of the risk due to the flood protection constructions that have been realized. Nevertheless, in many low and middle income countries, the high exposure overlaps with poverty and vulnerability. And in this context, there is there are much lower standards for flood security. So it seems that there is also not only an issue with the flood risk and the flood impact, but there is also a ethical issue because there are countries that have less tools to protect their territory that are most exposed. Let's see some statistics. Of course, we can deal with pluvial flooding, flooding, coastal flooding, and here there are some examples just to quantify those type of flooding and the impact of those floodings in general in terms of millions of peoples. For instance, if we take a look at the population exposed, the absolute number of people exposed to flooding is living in China and India. This is a matter of law of the large numbers. If we look at the percentage of population, India and China are not anymore the ones in the worst situation, but there are countries that have higher risk, like Netherlands, Bangladesh, Vietnam, and so on. If we take into consideration the pluvial flooding, in the pluvial flooding we recognize the presence of the Philippines, where apparently 23% of the population in Philippines is exposed to pluvial flooding. So in principle, we have for sure some trade-off between flood risk and population distribution, as well as the way the population is protected. Because, for instance, in Netherlands, even if a significant amount of population is located in areas which are potentially exposed to flood risk, they are significantly protected with flood protection systems that are designed for extraordinary flood events. An additional interesting perspective and point of view is provided in this manuscript by Linderson et al. Of 2023, where the authors analyzed the trade-off between major floods events and an index which is identifying the economic disparity within a country. And in particular, they identified the disparity or inequality across different countries, and discovered that there is a strong correlation between the impact of flood events and flood fatalities with this inequality index. This somehow means or implies that the economical overall situation, the economical condition of a country might discriminate the level of impact of each flood event. Now, to look at this in perspective and try to identify what might happen in the coming 100 years, there is another study that tries to project the future flooding in a RDCC scenario and try to identify how the flood risk may change over time. What has been identified in this manuscript is essentially that there are two factors that might affect flood impact and flood risk, and one for sure is climate, but the other one is for sure population change. And as we can see from the graph, these authors identify the population change as the main driver. So This might be particularly true in developing countries where the population growth is more significant. In countries like Europe, where the population is more stable, this issue doesn't exist. But in other countries, it may exist. And in fact, we see the projected change in population exposed to flooding in 2100 may increase of 0.3 billion of people. This actually has some difference across countries, and what has been observed is that low income, low GDP urban areas show the steepest growth in exposure, and urban exposure raises of about 33%, which is also extremely significant and somehow is an element that is suggesting how the urban expansion is somehow modified and taking part or using part of the land that might be exposed to flooding. Now let's come to the solution and to the strategies for flood mapping. We do have traditional strategies that can be carried out. We have flood mapping, we have flood modeling, we have hydrological modeling, and this is extremely useful for this task and has a great potential to help and support flood assessment at a large scale. There are significant attempts to build flood models at global scales with successful results. Still, some uncertainties are still there regarding the implementation of infrastructure, the implementation of the behavior of hydraulic defenses, the implementation also of the hydrological information, especially taking into consideration the fact that the hydrological information is lacking in many parts of the world. We do not have so much hydrological information regarding the entire world. And this is particularly true and is well depicted in this map of the gauge station distributed across the globe, provided by Harold Moton in 2011, which is still realistic and is one of the aspects that I think is most critical. Nevertheless, we do have strategies, we have alternative approaches, and we have many studies that are building new knowledge in geomorphology, which can explore and can exploit information regarding morphology of the rivers. In particular, building upon the principle that flood-prone areas are subject to hydrological processes and hydraulic processes of the erosion and deposition that are driven by hydrology. It is very likely that we may have a strategy to read these signatures in the landscape and be able to depict, just starting from the landscape, to depict the flood-prone areas, and which this is also been boosted with the introduction in the web, in our literature and so on, of a huge number of digital elevation models. The number of digital elevation models is increasing over time, is increasing in level of the details, is increasing in resolution and also spatial accuracy. And there are also studies that are also correcting and building specific products that could be that are specifically developed for hydrological application. For instance, HydroShed is one of them. We have tandem X global DM, which is provided at the resolution of 12 meters, which is also has been proven to be extremely relevant for hydrological applications. Therefore, based on this global information, DM, there have been the development of several models, hydraulic models, geomorphic methods, and several others that have been developed worldwide to build and to support flood mapping at a global scale. Now, in order to understand this topic, in order to better identify the potential of these methods, we should start from the beginning and start from the research question that guided the authors of these models for global flooding to better understand the principle that have inspired the definition of these methods and also the outcomes. So first of all, let's start from the research question that have been driving us, such as is there a measurable topographic attribute that reveal flood exposure that can tell us something more about the flood exposure, which is the geomorphic feature that best identify valley bottoms and floodplains. Can the EMs support a simplified and repeatable method for flood-prone delineation? Can method be applied reliably at a large scale? What is lost when resolution scale changes? So all these issues will be somehow addressed in this presentation through the review of a number of work that have been carried out during the last, let's say, 15 years, more or less. Let's start from this first exercise, which was aimed to test three different geomorphic methods that have been developed between 2011 and 2006 and 2012. The first one is the modified topographic index. The second is the linear binary classifier, which is a method that actually developed and tests the different geomorphic features for the identification of flood-prone areas. And finally, the hydrogeomorphic method binary, which provides a simplified simulation of the flood wave. Now, the topographic index is a very simple index. It's based on the concept of the topographic index introduced by Bevan and Kirby in 1979 with a small modification, which is essentially the introduction of a new parameter. That is the exponent 10 in the contributing area per unit contour length. Introducing this factor, the index seems to be more reliable. Then the second method was based on the use of these three features: contributing area, surface curvature, local slope, distance of each cell from the nearest stream, relative elevation to the nearest stream, H, which is also named hand parameter. And finally, the GM3, which is a G-space procedure, which implementing a set of the terrain analysis to delineate the flooded area using an hydraulic depth that is scaling with the contributing area in each pixel of the channels that is investigated. Using these three parameters that have been compared with a simple metric, the metrics adopted for the comparison of these methods are usually the confusion metrics, where the rate of true positive, the rate of negative, the true negative rate, false negative rate, and false positive rate are used to assess the accuracy, the specificity, and the sensitivity of the methods. And based on in order try to amplify and to enhance the accuracy of the methodology, the method have been applied over a single catchment, which was the Tiber River, and based on this application, we actually obtained different results for two catchments that have been considered. In particular, we used the upper river, the upper Tiber River that was has an extension of about 5,000 square kilometers, and the Chiascio River, which is a subcatchment of the Tiber River, was much smaller, of 700 square kilometers. Then, looking at the performances are displayed both in terms of maps and in terms of matrices, indices of performances. We can observe that modified topography index, which was a simple method, has a very high true positive rate in both catchments. Nevertheless, the sum of the rate of false positive and false negative was higher for the topographic index and was smaller for the single feature binary classifier constructed based on the parameter h. While the performances obtained with the hydromorphic method were better in the small catchment, mainly because probably there might be an issue of scaling of the hydraulic radius of the water depth along the entire catchment that might require an additional parameterization. Nevertheless, this was a first attempt to work on geomorphic feature and to understand which one was performing better. We understood that there are methods that were promising, and especially the single feature binary classifier was promising, and also the topographic index that we further investigated in terms of reliability and scaling behavior, and we realized that the scaling behavior of this index was able to be less sensitive to resolution up to a scale of 100 meters in terms of cell sites. Therefore, based on an application on the Arno River Basin, we decided that the resolution that could be addressed with this specific index was generally of the order of 100 meters. This essentially might be true because we were dealing with a mountainous catchment where the need to have a very detailed resolution is probably lower than what we need for lowland and a flat catchment or an outlet, for instance. Therefore, we started to test different matrices, and among the many matrices, we also started to combine the features of the catchment among them, and we reached one specific features that we identified as the best performing, that was the logarithm of HAS, which is somehow the scaling function of the water depth along the river network, and the parameter h, which was identified among the combined feature the most reliable and the most powerful predictor for flood risk assessment. This is testified by the comparison of the performances of the single feature compared with the combined features, and here we can see that the best feature that was the H index compared to the logarithm of H of AT divided by H was outperformed by this combined index. So we decided that this combined index was reliable, able to describe properly flood-prone areas, and we named this combined index the geomorphic flood index. This geomorphic flood index somehow is the ratio between HR, which is the water depth in the river, and H, which is the position of a point respect to the point of the river hydrologically connected to this point. Therefore, if we have these two information, we can also derive from these two information also the water depth in each pixel of my catchment. And this powerful tool was recognized as a significant tool or relevant contribution to hydrology because has now been adopted and used in several countries and mentioned in several publications worldwide. How it works, how it is applied and developed. It is applied and used in a linear binary classification where we iteratively identify different thresholds on the geomorphic topographic index, which are used to binarize the GFI index to compare this GFI index with a reference flood-prone areas in order to optimize and to make this flood-prone areas more realistic and more comparable with the original one. Therefore, the final results. Final results is something like this, like we see this application in the United States, where the entire United States have been investigated and described in terms of flood-prone areas, GFI derived flood-prone areas, and as we can see, with the hydraulic mapping provided by FEMA, there are also still now some gaps in the delineation of flood-prone areas, at least at the reference scale of this type of investigation. So with an index like this, which can be derived only using digital elevation models, we can overcome these gaps and fill these gaps, providing full coverage of the flood-prone areas. We also developed, in this context, a tool for this type of application, and the tool is named GFI tool, which is a QGIS tool that uses the DEM along with a field DEM, the flow direction map, and the flow accumulation. Requires the setting of the threshold for the identification of the river channels, along with also the scaling exponent of the hydraulic water depth within the river. And based on these features, and also having as a reference a flood-prone areas map, it could derive the threshold of the method as well as the flood-prone areas. Let's see an example. Here is a run of the method, and here is a reference hydraulic map. This is, for instance, the final GFI, and this is the flood susceptibility. So all the flood-prone areas based on this reference map that have been used for training, which is, for instance, gives us the clear evidence of what is the advantage of the methodology, which is able to provide a full coverage of the flood-prone areas over within the entire catchment and within each reach of the river basin, which is something that might be particularly useful for any hydrological application. Now, let's see what came next. After this application, so we moved for a bit forward. And what has been done is essentially trying to develop something that was even better, identifying the limitation of the methods, identifying some of the errors that we were encountering. We realized that the method was not performing well in the confluences, because in the confluences there might be an effect of the backwater from the main river that might be responsible of the flood in the subcatchment, especially at the confluence. So we modified and tuned a bit the methodology, refining the way the GFI is computed in a pixel close to a confluence, measuring rather than the water depth in the reach, the water depth in the close main river. And in this way, we take into consideration the relative water depth of the main river in order to take into account the potential backwater that might produce a flooding in the confluences. By introducing an iterative process that corrects the GFI through this assumption, we actually improved the rock curve of respect to the observation. As we can see, the rock curve of this new index defined GFI 2.0, which was just recently published online, which is available. We didn't provide the codes yet, but will be available soon. It's improving a lot the rock curve. And I remember that the rock curve provides the true positive rate respect to the false positive rate, which means that the reducing this area above the curve implies a significant improvement, an improvement in the overall performances of the method. This is an example of our application and an example of how the methods behaves. And in particular, we can see that the flood depth distribution of the method of the GFI 1.0 provided a significant number of artifacts, and in particular, what is most interesting for us is the comparison of this figure respect to this one of the confluences, where we can clearly see how the impact of the backwater has been taken into consideration, and also the lake that is represented in this graph that we see on the top, on the inset on the left of the screen and in the middle of the image, where the abrupt changes, which are unrealistic and artifact of the calculation, have been totally corrected in this second image. But what is the most interesting is essentially what we see in the confluences and also in this second image, which is much more realistic. Now, if we have a realistic pattern of water depth, we can also use the water depth to move forward the methodology and try to map not only the flood hazard, but also map the flood risk, the flood damages, and provide an approximate estimation of the potential economic losses associated to a specific flood. Now, the methodology that we developed and the geomorphic flood index could be manipulated mathematically, and this mathematical manipulation can lead to an expression that allows us to quantify the parameterization of the equation of the GFI, and based on this parameterization, inverting the equation, we can derive the water depth in each point of my river basin. This is an example of application of this geomorphic derivation of the water depth. And this is the DM that has been used in order to derive this flood water depth, which has a linear correlation that is more than 90% respect to in terms of linear correlation respect to the an hydraulic simulation, and with a root mean square error of the order of 0.3 in the 2D domain. If we have the flood depth generally could be, and is the most significant feature that is responsible or that can be connected to flood damages. And based on this metric, we can actually quantify and apply the methodology over large scale. An application like this was carried out in Romania, where we have been able to map and describe the flood depth distribution associated to each river of the country, and based on a damage curve available and applied over the entire territory, based essentially on land use and definition and presence of urban areas, it was possible to define a vulnerability degree in each area, and also work at the urban area in order to estimate the economic potential losses per square meters based on the water depth and buildings exposed to flooding. This is one of the outcomes, and of course, this is one of the potential application. With this methodology and these methods, we could reach refine and a simple and a preliminary description of the flood risk. We can also build a preliminary mapping of the priorities in order to plan future investigation and more refined investigation over my territory. And the methods could be extremely useful also for insurance companies in order to assess a preliminary estimate of the values exposed to flood risk over large areas, just using geomorphic feature. I have to say that this is, of course, still evolving. It contains a lot of potential, but it's certainly a great tool to start with. Now let's come to an additional brick in this research, which is represented by the use of satellites, because we now have DEM-based feature, but we can also enrich our information and data with satellite data, such as passive sensors, active sensors, and so on. And by using this, we first of all we investigated the potential use of spectral indices in order to build and assess the reliable detection of water surfaces and flat surfaces using multispectral indices. Essentially, these indices and this approach can be extremely useful for several applications: emergency purposes, flood risk assessment, rapid cost-effective observation, and so on. In this work, we reviewed a significant amount of literature, and we identified the most relevant multispectral indices that could be used for flood mapping and water body mapping. Essentially, within this work, we could identify the most frequently adopted satellite, which is for the optical satellite passive sensor, is represented by Landsat in most of the cases, especially more recently, and also the multispectral index that seems to be more reliable in terms of detection, with MNDWI that reaches performances and accuracies of 93%, and the MD, MI with at 93% and the NDWI at the 87%. Now, the most used ones are the first two, which have also the highest performances. Um, let's go to an example of application where the multispectral indices coupled with other information have been used to map floodplain areas in different areas of the world, providing reliable results. But this is not the only application, because we also developed an additional approach based on SAR data, and essentially we coupled SAR data with ancillary data, in particular with the use of geomorphic flood index, to build a Bayesian approach for the detection of flood-prone areas. And in particular, we use a combined approach where multi-temporal SAR data is acquired in order to detect relative change in the SAR signal, and this information is coupled with the information retrieved from the GFI that provides a reference threshold of potentially flooded areas, and the two provided a significant enhancement of the quality of the overall performances of the flood mapping. All this information, of course, provides a significant amount of data that could be used potentially to further enhance our capacity to predict flood events. And here it comes the use of the artificial intelligence. The artificial intelligence is a new trend where new solutions can have been implemented in order to build new models based upon our current data and exploit to the maximum available data. Of course, there is always the risk to over-parameterize a model and overfitting a model based on artificial intelligence. Therefore, it's critical to have enough data for training. Now, there are a lot of potential in the use of AI for Earth application, and those type of application can be beneficial for the entire human society and the Earth system. Of course, there are also some critical aspects that are connected to the regulation in the use of AI, but of course, here in science, especially in environmental science, we are trying to do our best to use AI for good purposes. In our case, we can get we can carry out real-time forecast for events like flood or droughts, make large-scale analysis integrating multiple data sources, support water management optimization, identify anomaly, and have a cost and time efficient method. Of course, there might be some limitation in the fact that we have an influence and dependence on data quality. a strong need for calibration, and issue of initial and maintenance cost, which is also which might increase over time with the increase of data availability, and the uncertainty connected to extreme events and extreme climate, where we do not necessarily have reference data to test the model. In particular, for our application, we adopted a random forest model, which was introduced by Breman in 2001. It's a commonly used approach for many machine learning methods, and it's in most of the cases very promising, very efficient as a method. In particular, in this machine learning method, we used a number of features for the training, and we also trained the method using remote sensing observation and all available flood events that we could retrieve over our area of interest. The method is based on the construction of a number of layers and features that could be used for training. We use for the training a number of a subset of 70% of the observation, and we left 30% of the observation for the final validation. And then these are the rock curves obtained over the training area, and this is the final result. Now, just to have an idea of what is the methodology and how the methodology is developed, is we actually introduce in our method the flooded and non-flooded areas, and in particular the marginal hazard areas. Based on floods and based on observation of floods, we derived a subset for training, which was somehow connected to the flooded area. Since floods are not observed over the entire territory, we have to identify and discriminate the territory hydrologically connected to this river network in order to be able to discriminate those territory where we have information from those where we have no data for now. So in this case, the distinction has been done following this approach, and the data for the calibration has been retrieved from remote sensing observation. For now, we tested and carried out our analysis only on the Italian territory, but we are expanding our studies because there are global archives and global database about floodings that could be potentially adopted and used. And by using this all this information, we actually could develop a flood inventory of about 208 events at the national scale, and coupling this information with different factors such as the GFI, the distance to the nearest river, the mean maximum daily precipitation, and so on, we actually identified the most significant, the relative importance of the conditioning factors, and we trained our model in order to reach the new flood susceptibility map, which was published on Stoten this last year, really a few months ago. This is our last result, and is also our final direction, because we are fully convinced that machine learning can be a strategy for flood mapping, combining machine learning with geomorphic features. It can help us to maximize available observations on geomorphology from one side, and flood events and occurrences And in this way, we can both take into consideration the dynamics of the flood process as well as the occurrences of the flood processes, because moving and with the evolution of time, we will have an increasing number of observation of flooding taken from satellites that might be extremely helpful to update timely flood exposure of our territory and build a method that could be also sensitive to climate change, climate evolution, also urban evolution, and eventually provide a significantly complementary mapping system for flood risk. With this, I think that I can close with takeaway messages. In particular, what we have in our hands are tools such as the GFI 2.0 that provide a static vision of the flood susceptibility of an area. We have developed plugins that could be used, tools developed in MATLAB. We investigated the downscaling effects. We have we are working on the development of inventories of flooded area that combined with machine learning will and are building new knowledge regarding the flood dynamics. And by working on these inventories and building a large partnership, we can probably build more reliable and a fast-growing method and more reliable methodology for operational uses. With this, and finally, I would also to thank my research group that is supporting our research activities, and in particular, there is the flood group where there is Jorge Navarra Saavedra that is focusing specifically on this topic, along with Ruodan Zhuang, which is also working on this topic with many other colleagues such as Caterina Samela and many others that have been supporting us in these activities. By thanking you, I open the ground for questions and any comments. I know that if the presentation is going, I may not be able to be present, but this is just the opportunity for me to thank you all for giving me again the opportunity to be present in this excellent event.